Welcome back. So to pick up where we left off last time, we looked at some very simple computational models, including a finite state machine, and then we made it a little bit more powerful by giving it a stack. And now we're going to look at the most powerful, if you want to look at it that way, computational model, Turing machines, which is basically what we mean when we say algorithm. If you talk about an algorithm, or if you even talk about a modern computer, a computer is just a bunch of AND gates, NAND gates, AND gates, OR gates, etc. In fact, all the way down to the processor level, it's just a bunch of zeros and ones and a bunch of ands, ors, nots, etc. So the Turing machine kind of captures that notion in a mathematical sense. In particular, there are 7 parts to this rather than a finite state automaton that only has 5. Basically, in addition to state transitions and stuff like that, you also have access to what's called a work tape. So the Q is a set of states. It's still a finite state machine. In other words, it has a finite number of states that it can be in. This is an input tape, alphabet. And this is an output tape, alphabet. Now, usually, we're going to go ahead and say that they're both equal and that they're both binary, right? But basically, the idea here is that even though the input alphabet tape, this is read only, this is read and write. So it turns out that if we can actually write stuff down and have output just like a queue or a stack, it turns out to be a lot more powerful computational model. And just as a technicality here, with a finite state automaton, you could only read the input once. Well, we've relaxed that condition on the input tape for a Turing machine. It can go back and forth and reread it as many times as you want. That's not that big of a deal. That's actually not that big of a change. Because once you have an output tape, what you could do is if you're only allowed to read the input once, well, you could go ahead and copy it to the output tape and then read it as much as you want. So it's not that big of a restriction. But here the transition function is much more complicated. This is the current state. This is what you're currently reading, input, reading input. And this is what you're currently looking at as output, current output bit. So given the current state, given the current input bit, and given the current output bit, go ahead and transition to a new state. Rewrite the output bit. And if you don't want to rewrite it, well, you can just, if it's a 0, then go ahead and write a 0 again. If it's a 1, you can go ahead and write a 1 again. And then transition both tape heads. This is move left, right, or none on both input and output. Okay? And then, of course, you have an initial state. Then you have a single accept state and a single reject state. So with our finite state automaton, we denoted this with just a circle, or the accepting state, we did a double circle. Here, we're just going to have one universal accept state, one universal reject state. Okay? So the picture looks something like this. You've got this input tape. This is the input tape, if you want. I believe that they call it tape because way back when Alan Turing came up with this model and this idea, that's basically what they had, maybe. But you have this tape where there's the input, x1, x2, x3. Remember, these are all just bits, right? You have this output tape as well. y1, y2, dot, dot, dot. And not only is it an output tape, but it's an infinite output tape. Whereas the input is always going to be finite, you're allowed to write as much as you want off to infinity. So to denote whether or not you've written something, is 0 or a 1, we use these special symbols to indicate blanks, that they're unwritten. And you can also write them if you really want to, but they're just these things right here. Right? In fact, these are used all over the place. In a typical text editor, you can't see if there's the difference between a tab and 5 spaces or something like that. So what happens is you can typeset them as these special symbols that show that this is 1 space, this is 3 spaces, this is 1 long tab or something like that. Have you seen that before? Yes? No? Okay. Well, you might see that eventually. And I think that it comes with this, or we use this because of this convention over here. So you've got an input tape, you've got an output tape, infinite, and you've got this finite state control. The finite state control is looking at a particular bit in the input. It's looking at a particular bit in the output. And then it makes this decision. There's I don't know, 50 states in here or something, however you want to design the machine. You've got 50 different states in here, given the input, given the output, given the current state that you're in, transition the output, transition to a new state, and then either move the tape head left or right on the input, and move the tape head left or right on the output. You can read as much as you want from the input, but you can't write to it, because then you'd be overwriting the input. But you can read and write and overwrite as much as you want on the output tape. Okay? So you can kind of see how you might, like this is kind of like a very rudimentary processor. Of course, you could take any high-level programming language and simulate this kind of machine. But you could also write any machine to implement any algorithm that you want. It's just that this is even much lower level than even machine code. Right? Remember back in the day when you didn't have compilers or anything, you actually had to use punch cards and program in binary. Right? This is basically even worse than that, because you don't even have the luxury of a machine language and a set of instructions that you can call. You have to come up with all the instructions. Okay? So as an example, let's design a Turing machine visually to solve that one problem that we had before. Remember that this is our language, that there's no finite state automaton to decide this language here, such that n is an integer greater than 0. Right? Where there's an equal number of zeros and followed by like say 2 zeros followed by 2 ones. If there were 3 zeros followed by 2 ones, it would not be in this language. If there were 8 ones and 50 zeros, it would not be in this language, etc. They have to have the same number of zeros followed by the same number of ones. And you can't interleave them. So 0, 1, 0, that's not in the language either. Right? Remember, at a very high level, what we did was we used a stack. We said, all right, continue reading zeros. While you continue to read a 0, push it into the stack. And then the second that you see a 1, start popping them. And if you pushed 5 zeros, you would expect to pop 5 ones, or pop them. If you saw 5 ones, you would expect to pop them all out. At which point the stack would be empty, and you could say, yes, that's in the language. If anything went awry, then you would say, no, I'm going to reject that string because it doesn't conform to this. Right? We're going to do the same thing with a Turing machine. Okay? I'm going to start with an initial state. Okay? Now, in this state, when I start out with this state, if I see a 1, right, no zeros at all, and I immediately see a 1, should I accept or reject that string? 1, 1, 1, 1. Is that in this language? Nope. So I will jump to my universal reject state. And by the way, the universal reject state, that's when the machine stops. When does an algorithm stop? When it outputs its true, when it outputs the path, when it outputs whatever, it stops. A Turing machine stops when it goes into either its reject state or its accept state. Okay? So when I see a 1, it doesn't matter what I see. This is the input. this is the output. It doesn't matter what I see in the output, so I'll just use a dot to denote that. If you see a 1 on the input, right, this will be input and output. All right? Then I'll go to this state and I'll reject it and I'm done. Okay? Also, I said that it has to be greater than 0, so if I see nothing, right? If I see nothing at all, it's an empty string, then I'll go ahead and reject that one too. Otherwise, if I see a 0, and it doesn't matter what I see on the input, I will go ahead and go to this state over here, Q1. Okay? This is my while loop, the start of my while loop. While you see zeros, stay in this state, and on the output tape, what we'll do is we'll write initially we'll write a special symbol. All right? Here's my output tape down here. Right? I'm going to use my output tape as a stack. Okay? So what I need to do is I need to know when I'm at the beginning of this output tape. So what I'm going to do is I'm going to write a special symbol here. Remember, we said that we're going to restrict our retention to binary, but when I talk about it at a higher level like this, it's kind of useful to have some special symbols. So when I go to this state, I will write on the output tape a hash. I will do nothing with the input, and on the output tape I will move, I'll move right. Okay, so to annotate this, if you let me go ahead and go over here. If a 0, then mark the output with a hash. That's just so that I know where I began, and then move the output tape head right. And then this one is leave the input tape head alone. All right? That's how you're going to interpret this. So on the input tape, say, I'll draw an example input here, 0, 0, 0, 1, 1, 1. Okay? Here's my output tape. And here's my finite state control, which is really small, which is actually up here that I'm drawing, right? So initially it points over here, then initially it points down here. I write this hash symbol, and then I go on to the next cell. Okay? Now once I'm in this state, that means that I'm reading a bunch of zeros. So I want to stay in this state. Again, this is kind of a while loop. While you read zeros, I'll stay here. While you read a 0, and it doesn't matter what the output tape is, because of that I'm writing to it, I will write a 0, and I will move the input tape right and the output tape right. So as you're seeing zeros, go ahead and write a 0 and move to the right. Move to the right. You see a 0, do another 0, move to the right. Move to the right. As you see this 0, move to the right, write a 0 and move to the right, move to the right. Now my input tape is pointing here. Okay? All this is doing is, as long as you see a 0, write those zeros, copy that over here to your output, because this is basically serving as my stack. Right? Push a 0, push a 0, push a 0. Okay? All right. The very first time that you see a 1, right, and it doesn't matter what the output is, because we haven't written to it yet, what I'm going to do is I'm going to transition to a new state. Now what I want to do is I want to pop, pop, pop. Right? I want to make sure that the number of 1s is equal to the number of zeros here. So if once I've seen a 1, what I will do is I won't do anything with the tape heads. I'll leave those alone. I'm just going to transition to a new state here. I don't want to move these two heads. I just want to leave them here and leave them here, and then I want to pop, pop, pop. All right? So what I'll do in this, this is 2. Right? There we go. Once I see a 1 on the input and a 0 on the output, then I'll stay in this state and basically pop it off. I won't overwrite it or anything. Well, that's what I'm doing over here, I guess. I'll overwrite it with a blank symbol. I will move my input tape head right, But what do I want to do with my output tape head? I want to make sure that this 0 matches this one. This 0 matches this one. 0 matches, matches, matches. I want to work in opposite directions. So my input tape head will move right. My output tape head will move left. Okay? Until what? Q accept. There we go. When do I accept? Then I would accept this one because 0, 0, 0, 1, 1, 1. So 0 matches, right? 0 matches, 0 matches. And I'm at the end of the input, which is going to be a blank symbol, and I've come all the way back to my original hash mark. So the second that you see a blank symbol on the input and the hash symbol on the output, the empty symbol on the input and the hash symbol on the output, then you're done reading all of this input and you can go and accept it. If, however, anything else occurs, for example, what if I have 1, 1, 1, 1, right? And I only push 3 zeros? Then that means that I would have seen, I'll go down here, I would have seen a 1 in my input and in the hash, there we go, on my output, right? My output tape head got to this hash, but I still have 1s to read, right? So I would go into my universal reject state over here. What's another situation that could occur? This was where there's more 1s than 0s. What if there were more 0s than 1s? What would it look like then? I would have pushed a whole bunch of 1s, gotten to the end of my input, which would have been, the end of the input is going to be a blank symbol, but you're not seeing a hash over here, you're still seeing zeros, right? More zeros than 1s, so reject. Right? Is there any other condition? What if it were instead 0, 0, 0, 1, 1, 1, then another 0? Then what would you accept or reject that string? Is it in my language? Nope. So if after seeing all the zeros and writing all the zeros to your output tape, then you start seeing 1s, if you ever see another 0, and it doesn't matter what's on the output, go ahead and reject that. Right? Now that's a nice pretty picture, right? It's deciding a very, very simple language. But if you really want to program something like this, you'd really have to get down to the nitty-gritty, and that's what I did exactly in the notes at one point. There's the actual program, right? This is worse than binary, right? If you were to actually program this, say, in C and compile it, I'm sure that it would be at least a few K, or at least 2K or something like that to handle that. And so it would be larger than this in pure machine code terms. But I had to define every single transition. And this was for only 3 states with 2 universal accept and reject states. Imagine if you had a much more complicated problem where you had 50 different states. Are you going to program this? Program it like this on a piece of paper? Definitely not. That's why it's more of a way to speak about computability in theory, right? But still, this is exactly what you do when you design a processor, right? Has anybody already taken 230 or 231? No? Okay, well, you'll get down to the nitty-gritty where you may be designing a processor from the ground up. You have to design a circuit to do addition, right? You have to design a circuit to do addition of 2 4-bit numbers, right? And then you can generalize that, and of course you could build a circuit to do addition of 2 32-bit numbers. And now you have the beginning. You maybe want to design a circuit so that you could load a number over here and then load a number over here and then read and rewrite those and then combine that with your circuit down here to add them together and put this into another location. And now you've got the beginnings of an ALU, an arithmetic logic unit, where you've got, say, 3 registers and an adder right here. Right? This is how processors are actually built. You build simple little tiny modules and then you tie all those modules together. Right? And that's why it's extremely complicated. You have to get down to the really low-level kind of stuff like this. Right? But that's a basic Turing machine. So what does it mean for a Turing machine to decide a problem? Right? Remember, all the way back at the beginning, what did we start with? This statement. Algorithms solve problems. I translated each one of these things. I translated problems into languages. We've now translated algorithms into Turing machines. So what does it mean that solve means decide? And that's the easiest one. That's why I save it for last. Right? Definition. A Turing machine decides a language L if and only if for all inputs X which are, again, strings, binary strings, T of Turing machine M, we'll call it M, T on M, M on X, sorry, right? This is a machine M run on input X. Always halts, and for every X in the language, it halts in the accept state. For every X not in the language, it halts in the reject state. All right? Now, these two conditions are pretty straightforward. Obviously, a machine is going to decide a language if it rejects strings that are not in the language and accepts strings that are in the language. We did that with finite state automaton. But the other condition here, the more important condition, is that it always halts for all inputs. Right? Now, is this true of all programs? Does every program terminate? No. Who here has not written a program that got caught in an infinite loop? I better not see any hands. Everybody does this at one point. And in fact, you do this intentionally sometimes. Right? Have you ever heard something called a poll loop? Right? When you turn on a computer and it's sitting there waiting for your input, what is it doing? It's going in an infinite loop. It's polling. Is there any input yet? Did you move the mouse? Did you type on your keyboard? Is there any input for me to process? Right? Window managing systems, they do this all the time. They're stuck in a big, giant, infinite poll loop. The only thing that terminates that infinite loop is you shutting off the computer. Hardware does this all the time. It asks for interrupt requests. It'll ask, does channel 5 want to start speaking? Does channel 6 want to start speaking? Does channel 7 want to start speaking? Then it goes back to the beginning. Poll loops. Right? So sometimes infinite loops are necessary and useful. Right? But with respect to a Turing machine, if a Turing machine gets stuck in an infinite loop, then it does not decide that language. Right? It only decides a language if it always terminates on every input and says yes or no by going to an accept state or a reject state. Okay? That's what we mean by these three things. Algorithms solve problems means that if you've got a problem, if you've got a language, can you come up with a Turing machine that decides that language? That if you feed it, the input, then it'll say yes. This is a graph with a path between x and y. No, this is not a graph with a path between x and y. Right? It doesn't say, okay, well, this is a graph. This is x and y. While one do nothing, right? If it gets stuck in an infinite loop, then it doesn't decide that language. So now the question of can computers or algorithms solve any problem can be now translated now that we've got a mathematical basis for asking this question. We'll translate it to, for any language, and I'll flip it as well, for any language, L, is there a Turing machine that decides L. Right? I've translated the problem now to something that we can mathematically reason about. And remember, a language is a problem, a Turing machine is a computer or an algorithm, and solving means decide. Right? And the answer is a big, huge no. Right? So I'm going to appeal to your mathematics side and show you proof 1. Right? Fact. Turing machines are finite. Right? Here's a Turing machine that I just showed you. All it was a bunch of transition states. This is finite. There's only a finite number of rows here. If a Turing machine is finite, then you can encode a machine as a string. Right? In other words, something like this. Remember yesterday when we encoded a graph? Right? I gave you all the same arguments that at the end of the day in a computer, everything is just a 0 and 1. So a graph is just a string consisting of zeros and ones. Any finite object can be expressed as a bunch of zeros and ones. Express this as 0, 0, 0, 0, 1, 1, 1. Well, express this as 0, 0, 1, 1, and then this is, I don't know, 1, 0 or something. Right? Express each one of these things as a binary string. Right? In fact, even it's human readable here, but this was originally a PDF, right? So this PDF was just a bunch of binary sitting on a computer somewhere. So you can take any machine and you can compile it to a bunch of machine code. Right? You can take any program, any algorithm, and you can compile it to a bunch of binary. Right? So that's not that big of a deal. Right? Fact 2. Fact 1, fact 2. Strings are countably infinite. Therefore, all Turing machines, the set of all Turing machines, let's say it that way, the set of all Turing machines is countably infinite. Now, hopefully you remember what countable and uncountably infinite are. If not, we can do a really quick review here. But basically, the argument here is that i.e., you can order them. Right? You can order them lexicographically. There is a first Turing machine. There is a second Turing machine. There is a third Turing machine, et cetera, because strings are countably infinite. There's the string of length 0. There's all strings of length 1. There's all strings of length 2. ... Right? So if Turing machines can just simply be expressed as a bunch of zeros and ones, well, you can do the same thing. Just write them down. That means that they're countably infinite. However, fact 3. The set of all languages is uncountably infinite. All right? So my proof is going to be a simple diagonalization proof, which is a proof by counterexample. But before we do that, I need to make sure everybody understands what we mean by countably infinite and uncountably infinite. So the natural numbers. They're countably infinite because you can go 0, 1, 2, 3, 4, ... Z. There are twice as many integers because you have all these numbers plus all their negations, but they're still countably infinite. You can put them into a row and not miss any. 0, 1. What do I need to do to make sure I don't miss any? -1, 2, -2, 3, -3. Right? You can write it in one direction, basically. Okay? Q is countably infinite. What order do I do these in, though? Q is the set of all rational numbers, all A over B, with B not being 0. Can I write those in a line? So what if I go 0, 1, 2? Wait a second. What about that infinite number of values like 0.5, 0.75, right? Pi divided by 3. All of those, or pi divided by 3 would be over here, but pi divided by 4. There. Now we're over here, right? So how do I make sure that I don't miss any? The trick is to this is not diagonalization, but it's the same basic idea. Write A and B in one big tableau here, right? This is going to be 0 over 0, so forget about it. That's not real. This will be 0, 0, 0, 0, right? This will be, we can ignore these as well if you want to. In fact, we can ignore the entire, just write 0 first. And now this is 1 over 1, 1/2, 1/3, 1/4. This is 2 over 1, 2 over 2. Now we're repeating some things here. This is 1 and this is 1. That's okay. That's okay to repeat as long as you can get them into an enumeration. All right, we repeated 1/2 here and here. 3 over 1, 3 over 2, 3 over 3, 3 over 4, dot, 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 and then dot, dot, dot. All right? Now, here's my enumeration. I'm just simply going to go along all the diagonals. Right? And in fact, there's a simple calculation that you can come up with that would give you any number in this enumeration right here. Right? So even though there are an infinite number of elements in here, I can come up with a formula that tells you that in this enumeration, you're eventually going to get to that one. Right? Can you do that with R? All real numbers? No. And the reason is you can diagonalize it. This is Cantor's diagonalization argument that was, what was his name? Edgar Cantor? No, Gregor Cantor or something like that. George or Gregor or something like that. And when this was the first non-constructive proof, and it was rejected at the time, but pretty much it's universally accepted, and it's a powerful technique. Right? So here's my final proof. Right? My proof of the following fact, right? That languages are uncountable. Right? So, by way of contradiction, whatever. Suppose languages are countable. This implies that there is an ordering, say L1, L2, L3, dot, dot, dot. Okay? Now I'm going to draw them like this, L1, L2, L3, dot, dot, dot. And what I'm going to do is I'm going to draw all strings, x1, x2, x3, x4, dot, dot, dot. So these are these are the set of all strings, which is sigma star. And these are all the languages. Now what I'm going to do is I'm going to write a 0 or a 1. Right? So this is say 0, 1, 1, 0, dot, dot, dot. A 0 indicates that x sub I is in L sub j. And 1 is going to indicate that x of I is not in L sub j. And maybe I should have gone I and j but, to be consistent, but that's fine, right? 1, 0, 1, 0, 1, 1, 0, 1, dot, 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 and of course dot, dot, dot. Right? Now here's where the Cantor's diagonalization argument comes in. What he did was, and unfortunately I drew them all as zeros, is he went along the diagonal, right? Dot, dot, dot. And what he did is he constructed a new language. Actually, he didn't do this with languages, he did this for the reals, but it's the same basic argument. Here's a new language, L prime. L prime is going to consist of all x sub I such that L sub I rejects x sub I. Right? There we go. So this rejected it, or maybe just for variety here, I'll change this to a 1. Rejected it, accepted it, rejected it, accepted it. What we're going to do is we're going to do the exact opposite. We're going to accept it, we're going to reject it, we're going to accept it, whatever. We're going to disagree with every single language, right? And rejects does not include. Because a machine rejects, a language doesn't reject. Does not include x sub I. So in other words, I've created a brand new language here. Is it equal to any of these languages? Suppose that it is. By construction, I disagree with that language in the ith string. Because if that language accepts it, I reject it. If that language rejects it, or includes it, then I don't include it. If that language doesn't include it, I do include it. Right? So in other words, I set myself up to disagree with every single language in this supposed ordering, this supposed enumeration. So there's the proof. No such enumeration can exist. Right? As a consequence, there are more languages than Turing machines. Therefore, some languages, in fact, an infinite number of them, do not have any Turing machines that decide them. Right? And if that doesn't seem all that satisfying, you'd be in very good company with 19th century mathematicians who also rejected Cantor's original argument. Right? Fermat, I think, was one of them, or maybe it was Laplace rejected it and said, well, I can't find any flaw in your proof, but I don't like it because it makes me uncomfortable, because at the time, it was the first non-constructive proof. We didn't really construct a real language, did we? We just constructed this fake language that has no bearing on reality. Maybe it's not even a useful language. We just constructed it in order to make this argument. That there are some languages out there, we don't know what they are, but there's some languages out there that do not have any Turing machines that decide them. Right? So, let me give you a language that is useful, that is definitely not decidable. Okay? Here's a fact. No Turing machine exists that decides the halting problem. The halting problem, HP, is simply this. Given a Turing machine, so this is a different Turing machine now, M, and on input X, question, does M, when you run it on input X, halt or not? That is, it's an infinite loop. That would seem very, very useful. You could use this to statically analyze your code to see if it's going to get stuck in an infinite loop without even running it, right? You just have this compiler or this linter or this static analysis tool that tells you otherwise, right? But no such algorithm exists. There's no such Turing machine that decides this problem, right? Proof. Again, by way of contradiction, suppose such a machine, such a Turing machine exists. What I'll do is I'll call it H for the halting problem, right? That takes as input an encoding of a machine M and an input X, and it outputs one of two things. It halts and outputs 1 or true, right? If m on x halts. It halts and outputs false. In other words, it rejects if m son x does not halt. Okay? So by way of contradiction, I'm going to assume that such a machine exists. Of course, my original fact theorem that I'm trying to prove here is that no such machine exists. So if I assume by way of contradiction that it does exist, eventually I will get down to a contradiction. Again, by way of contradiction. That's the whole point of doing a proof by contradiction. Okay? Now, consider running a machine M on itself. That is, M on an encoding of M. Right? That looks kind of weird, but when you think about it, it's not weird at all. Right? You do this all the time. The usual example that I give is, so old Nintendo games, say Legend of Zelda or Super Mario Brothers. You really like to play them, right? Maybe, I don't know. Say that you want to play them. How are you going to do it? I guess you could go get an original Nintendo machine and a cartridge and blow on it and then get it to work. But how else would you play it? No? What? An emulator. What is an emulator? An emulator is a program that runs another program. Right? Emulators. They do this all the time. What else is a program that runs another program? Operating systems. Right? What is a program that runs an entire other operating system? Virtual machine. What is a virtual machine that runs an entire operating system?